So we'll start with some review questions from projectile motion and then move on to the next section, which will be relative motion. So okay, so this is a situation. So a projectile is fired like this. Now it goes and hits the inclined plane at some point P over here. So we have to find this distance. Suppose this is Z. So find Z. So just try this question. Okay, so let's go over the method here.
Sir, just a second. Sir.
Okay.
Just a second.
Yeah, go ahead. Try. I'm just setting up the coordinate frame and all that. Okay. Okay, so Akshat and Soham, I'll verify the answer. You have to take this distance as Z. Okay. So suppose I'm labeling this point over here as the point E. Okay. So this is a straight line now. Whereas this is the parabola. So the trajectory is parabolic. The equation of trajectory is here. So the straight line, it has a slope m of tan alpha, which is tan 45 degrees, so 1, and it passes through the point A, which has coordinates d comma 0 or 200 comma 0. So the equation of the straight line is of the type y is equal to mx plus c, where m is the slope, is equal to 1. C we have to calculate, but the point A, which is 200 comma 0, lies on the line. So we have 0 is equal to x, which is 200 plus c. So that means the value of c is minus 200. So the equation of the straight line here is becoming y is equal to x minus 200. So therefore, the point P, which has some coordinates x, y, satisfies both equation 1 and 2, because P is the intersection of these two. So basically you have to solve 1 and 2. So from equation 2, substitute y as x minus 200. In equation 1. So we have x minus 200 is equal to 4 by 3 into 1 minus x by 240. So this quadratic equation has to be solved now.
Sir, that will be 36,000, right?
Hmm?
That will be 36,000 x square minus 6x minus 36,000, right?
Just a minute, just a minute. Yeah. 36,000, that's correct. This one, no?
Yes, sir.
So this is okay so far, no? Right?
Sir, actually, I had taken the other form of the range equation. So like I'm just confirming.
Other form of the,
I had taken the other equation, the other form, y is equal to x tan theta minus uh, gx square
but
by
that will give you
q
the
square.
same thing. Still
Yes.
it should
So like I am getting a slightly different equation. So that's what I'm checking. Where's the mistake? Is it?
q square cos square theta, na? This one you've taken.
Yes, sir.
Y is equal to 4 by 3x minus, ये कितना हो जाएगा, half into 10 divided by 50 square into 4 by 5 square. Give you y is equal to 4 by 3x minus
1200 minus 5x upon 1200.
10x square divided by, this is
So 3 by
14.
5 square, right? 53 degrees is the angle. So
3 by 5, sorry, yeah. So denominator will become, so 10x square divided
180. 10x square divided by 1800.
1800. So yeah, 4 by 3x minus x square divided by 180. So that is giving you the same equation actually. If you take this thing like 3y is equal to 4x minus x square by 60. Okay?
Yes, sir.
And then you substitute this thing, na? Y from that equation as x minus 200. So again, the same equation you got here.
Yes, sir.
Okay, so let's just complete the solution. So we are okay up to here, right? This step is correct. Okay, so we are taking this to this side. So x square minus 60x, that's correct. Okay, minus 36,000 is 0. So x is 60 plus minus square root of 60 square plus 4 into 36,000 divided by 2. So x is 60 plus minus 36 into 10 raised power 2 plus 4 into 36 into 10 raised power 3 divided by 2. So that is where I can take again 60 common. Okay. So this will become 1 plus this will become, instead of this, it will become 40. So we'll have x is 30 into 1 plus minus square root of 41. Now x should be positive from the diagram. So we will not take the negative root, we'll take x as 30. Okay. So this will, sorry, 1 plus root 41. So we will take x as approximately 30 into 1 plus, now root 41 is very close to root 49. So it will be little bit less than 7. Let's just work out. So this value now will come as about 222 meters. Okay. So this point where the projectile is hitting this thing, its x coordinate is about 222 meters. So the y coordinate will become x minus 200. Remember that was the y coordinate. So it's about 22. Okay. And this angle is 45 degrees. Okay. So you can see that this was 200 meters. So this distance is about 22 meters. This is 22 meters. So our hypotenuse Z Okay, so very good, Soham. Your answer was correct. Okay.
Sir, but I did from different method. And later
Okay.
I thought that steps were wrong.
Which steps you did? Did you use time-based
Sir,
equations?
no, I took trajectory equation only, but I took x is equal to 200. So I
Acha. So actually what is happening now, it's so close now, the values, that you're getting approximately the same answer. You understanding my point?
yes, sir. Because that where the curve ends, I took that like a horizontal one, and in that triangle, then I found the z.
Okay. Okay. So in the equation of trajectory, you put x as 200 or?
Yes, sir.
Okay. So you'll approximately get the same answer, not exactly. No?
Huh.
Okay. Okay. Anyway, you understood the method now?
Yes, sir.
Okay, so this is a more tricky question. Okay, it's a JEE advanced level question. So this is like the more difficult type of application of equation of trajectory. Anyway, so hope this is clear to all of you. Okay, now we'll move on to another example. So this time we'll look at an example with projection from an inclined point only, or from a point on the inclined plane. So this is a 37-degree angle. Okay. And what we are doing is we are projecting something from here such that u is equal to 20 meters per second, and this angle of projection beta, let's say, is equal to is 60 degrees. It goes like this. So if it is projected at t equal to 0 and it hits this surface at the point somewhere over here at some time capital T, we have to find capital T and range. Find capital T, range R. Take the value of √3 as approximately 1.7 to the calculation, and G as 10 meters per second square. Okay, so Parv, let me verify your answer. Okay. So here, as we've discussed before, we will take a different coordinate system, right? We will take x-axis like this, and we'll take y-axis like this. So our acceleration due to gravity g vector is like this. Okay. So the initial velocity is u cos beta I cap plus u sin beta j cap. So our x component of initial velocity is becoming 20 cos 60, so that's 10 meters per second. And our y component is becoming sine 60, so 10 root 3 meters per second, or approximately 17 meters per second. Okay. So these are the two important things. Similarly, our acceleration is having a component of g sine alpha I cap and minus g cos alpha j cap. So x component of acceleration is becoming sine 37, so 6 meters per second square, and y component of acceleration is becoming minus 8 meters per second square. Okay. So these two values become important. So now at some general time t, if it has coordinates x comma y, x will become 10t plus 3t square. Okay. Or in general, you can say it is u cos beta t plus half g sine alpha t square. Okay. And y as a function of time will become 17t minus 4t square. Or in general, y is u sine beta t minus half g cos alpha t square. Okay. Yes, very good. Correct answers you people are sending. So now from these equations at t equal to capital T, you can see that the value of y is 0 and x is equal to r. So this is equation 1, this is equation 2. So from second equation, 17t minus 4t square should be 0. Solution will take. So that's one part, and now substitute that in the first equation, you'll get the range. This becomes a bit of a lengthy calculation, but still we can do it like this. We can take 4.25 common. We have 10 plus 3 into 4.25. That is Okay, so this is an example of projectile motion on inclined plane and how to use the system of inclined axis for this case. Okay. Yes, but in case of inclined surface, you can be asked to calculate this kind of thing, which is instead of maximum height, it is a maximum distance from the inclined plane. So you can be asked to calculate that, and that will be nothing but the y coordinates maximum. So second equation that we have, y is equal to 17t minus 4t square. We have to calculate its maximum. Okay, so hope that is clear now.
No, sir, actually, I was asking with respect to ground.
No, with respect to ground, it will not make sense to calculate the maximum height now, because see, the ground level is here. So here we don't even know what the, you're getting the point now, what the projection points height is from the ground, we don't know that. So how we calculate the maximum height from the ground? You understanding the point now?
Yes, sir.
Okay. So that is why in the case of projectile motion or inclined plane, if that type of question is asked, then instead of from the ground, the height, it will be asked that what is the maximum distance from the inclined plane. In which case that this y coordinates maxima has to be calculated.
Okay, sir.
What? Okay.
Sir,
Yes.
can we generalize an equation of trajectory for inclined projection?
Yeah, you can do that, but it's very complicated now, because the thing is that see, x and y are both quadratic functions of time. So you have to eliminate time between the two. It's a much more complicated equation. You're understanding the point now?
Yes, sir.
Whereas if you take the x and y axis horizontal and vertical, then your x is linear in time. No? It is u cos theta and t into t. So equation of trajectory is easy to write. Okay. So while we can do it, but it just becomes mathematically too lengthy. Okay.
Okay, sir.
All right. So with this, we now move on to the concepts of relative motion. Okay. So you'll see that there are few questions in HC Verma which have like relative motion or projectile motion with respect to moving object and all that. So those type of questions will mix the concepts of projectile motion that we've learned till now and relative motion that we're going to learn next. Okay. Plus there are questions which are only involving relative motion. So this is the final part of kinematics, the concepts of relative motion. So the idea of relative motion is that we should be able to write equations of motion for one moving object or moving particle in a reference frame which is itself moving with respect to ground. Okay. So this is involving equations of motion for a moving object or particle or whatever. With respect to, or what we say relative to, a reference frame which is already moving with respect to ground. Okay, so very simple example of that is, if you are sitting inside a vehicle that is moving with respect to the road or with respect to ground frame at a certain velocity. So your reference frame is moving in that sense. Okay. Let's say you are this person A who's inside this car that is moving at, let's say, 30 kilometers per hour. And there's another car B coming from ahead towards you at a speed of 60 kilometers per hour. Okay. So V1 and V2 are with respect to ground frame. That is the stationary ground frame. Then what will happen here? The velocity of B with respect to A's frame, how much that will appear to be? Can you tell me how much will B's speed look like to A?
90 kilometers per hour.
Yes, very good. It will look like 90 kilometers per hour towards him. So when we write the notation like this, we mean of B relative to A or with respect to A. So when we write B comma A, we mean the relative speed of B with respect to A, and that appears to be 90 kilometers per hour. Now, how we can justify this? The justification of this is very simple, that if you are sitting inside this car and there's this other car coming at V2 like this towards you. Now, suppose this is the situation at t equal to 0, and the distance between you two is t at that point of time. So after some time, what is happening? This car has traveled by a distance s1, let's say, and this car has traveled by a distance s2, let's say. So at time t plus, or at time delta t, let's say, s1 is equal to v1 delta t, s2 is equal to v2 delta t. So by now what has happened? The distance between them has decreased to some d prime. So you can see that d prime has become how much? D minus of s1 plus s2. It has become d minus v1 plus v2 delta t. So how much the distance has changed between them? D minus this thing. This is this become v1 plus v2 delta t. So that is why the speed of B relative to A will become the amount by which the distance has changed divided by delta t. So in this case, it becomes v1 plus v2. So it becomes 90 kilometers per hour. So this is the justification of this, okay? Because you are going towards that car and that car is also coming towards you. So the rate at which it's coming closer to you actually increases. It becomes v1 plus v2. So this is the phenomena of relative motion. We'll see another example also where the direction may be same also instead of opposite. So there we'll see that the relative velocity becomes the difference. Instead of the sum of v1 and v2, it becomes the difference of v1 and v2. But anyway, this whole idea of writing any parameter like velocity, displacement, acceleration, etc., of one moving object with respect to a moving reference frame. That is called the relative motion equations. Just make a note of the definition and this example. Okay. So another example before we move on to proper definitions. That
Sir,
now let's say this, yeah,
sir, can you scroll up for a second?
yeah. So this is the top view of a road. Okay, let's say, and two cars are moving on parallel tracks. So this time this car is moving at 80 kilometers per hour, and this vehicle is overtaking it at 120 kilometers per hour. So what is the speed of B in the frame of car A? That is, any occupant in A will see B at some relative speed. Okay, so what is this relative speed? So these are speeds in ground frame. So in this case, how much it is becoming? Yes, very good. नहीं, so हम do the calculation again, beta. 120 है और 80 है. Yes, very good. That's correct. So in this case, what will happen is this it will appear to be 40. Okay. Because what will happen is if this is at time t equal to 0, they are alongside. Now after some time, let's say t equal to delta t, A has reached here somewhere. But B has reached somewhere here, let's say, which is going at 120. So to the person sitting inside the car A, it look like B has gone forward this much, no? So this will be the distance by which it seems to have gone forward. So that distance, so you can see that in ground frame, A has actually traveled a distance of 80 delta t. B has traveled a distance of 120 delta t. But to A, it will look like move forward by a distance of SB minus SA. So 40 delta t. That is going to be your relative speed into time. Hence, the relative speed will appear to be 40 kilometers per hour forward or along the positive x direction. Okay, so just make a note of this. I'll scroll back to the earlier example also. Okay, so hope this example is clear. Just scrolling back to the earlier example once more.
It's completed.
Sorry.
Sir, it's completed. Earlier example.
Okay, so the second example is also clear to all of you. If anyone has a doubt, please let me know. Okay, very good. Okay, so now let's move on to the proper vector definitions for relative motion. Okay. So you look at what we call relative motion parameters. So now we are talking about relative motion in general, not just the two examples that we've seen before. And in general, it's a little bit more complicated because in the two examples we saw earlier, the two objects were moving along the same straight line. But that may not always be the case. Another example of it is like if you're sitting inside a moving vehicle and you're observing rain which is falling. So even though the rain drops might actually be falling vertically with respect to ground if there's no wind, but the fact that you're moving in a car, the rain will appear to be moving, slanted with respect to you. And you'll notice the faster the vehicle is going, the more it appears to be slanted. And also the faster the rain hits the windows of the car. So that is an example of relative motion, for example, in two dimensions, because the rain is falling vertically and your car is moving horizontally. So it's a two-dimensional relative motion. So for those kind of situations, how to develop the equations? So we have to first understand the relative motion parameters as vector quantities. Okay. So like we had started in kinematics by understanding the parameter called position. So here also we'll start by understanding the parameter called relative position. Relative position. So let us say we are saying position of B with respect to A. So we use this kind of notation that whatever subscript we write, if it is B comma A, it means position of B with respect to A or relative to A. If we had written A comma B, then it would have been of A with respect to B. So now imagine that with respect to my ground frame, which is this XYZ coordinate system, I have two objects which are right now at some given time, they are located over here and here. Let's say A is located here. So A's position vector with respect to my ground frame is this one. So this is the position vector of A with respect to ground. And similarly, my second object B is, let's say, at this moment located somewhere here. So these are the instantaneous positions of A and B at some given point of time. They might be changing. So a little while later or a moment later, they will not remain the same. But right now they are like this. So then in A's frame, what is the position of B? It is nothing but the vector with respect to A where B is located. So it is a vector pointing from A towards B. So in this diagram, this third vector over here, this only becomes the position of B with respect to A. So in this diagram, you can see that RA, it is the position of the point A in ground frame at some time t, let's say, at some time t equal to B. So RB is the position of B in the ground frame at the same time. Okay. So now what is RBA in the diagram? This is the position of B relative to A or with respect to. So now from the vector diagram, you can see that this vector RBA is nothing but the difference of these two vectors. You can see that in the diagram. They're forming a vector triangle. So RA and RB are drawn from a common origin. And the third one is the vector from the head of A to the head of B. So you can use triangle law for difference of two vectors, or you can even use parallelogram law. But you'll understand whichever law you use, that vector which we've drawn is the difference of RB minus RA. So now this becomes a vector definition. So for example, if at t equal to 0, E is located at the points 3, 0 and B is located at the point 0, 5 on the xy plane. Then find position of B with respect to A and position of A with respect to B in I cap J cap notation. And these coordinates are given in meters. And from that, find and that you will see is nothing but the distance between A and B. Okay, so just try this out. Note down this definition and then try out this. So two particles A and B are lying on the xy plane at some instant t equal to 0. So their positions are given in coordinate form over here. Instead of vector form, the question is giving the distances in coordinate form. Okay, just make a correction. This is 3, 0 and 0, 4. Instead of 5, make it 4. So they are lying at these 2 points on the xy plane. So we have to find the position vector of B with respect to A, and then also the position vector of A with respect to B. And from that, we have to find the distance between AB, which is nothing but modulus of this relative position. So you can do the example below by drawing a diagram and understanding it visually, or you can just apply the formula above. Okay, you can use either method. Yes, very good, Parv, that's correct.
Sir, what you have written near the highlighted box?
The doubt again, please. Yeah, Harsh, your answer is correct. Good.
So what you have written near the highlighted box?
Near the box. Position of B relative to A or with respect to. That's WRT with respect to. This one only, no?
Sir, outside of the box, that something N A.
Where? Achha, this?
He's
No.
asking below that one.
This one? Yeah. Yeah, Harsh and Siddharth, your answers are correct. Okay. So you'll notice something over here, which you'll also understand when you do the previous, when you do this question. You see that R of B with respect to A is RB minus RA. But similarly, if you're calculating R of A with respect to B, it is RA minus RB. So, you know, that is the opposite vector of this. So position of A with respect to B is equal in magnitude, but opposite in direction of position of B with respect to E. So this is something you'll realize when you do this question below also. So one way of doing this question is no need to draw any diagram and all that. You can just convert it to vectors. Position of A is 3 I cap in meters. Position of B is 4J cap in meters. Okay. So from that you can see that position of B with respect to A, applying the above formula, is minus 3 I cap plus 4J cap. And the position of A with respect to B is this vector minus this vector, so it is 3i cap minus 4j cap. And therefore the distance between them can be expressed as magnitude of either of these two vectors, which is 5 meters. Now this whole question we can also understand it visually by just drawing a diagram. And if you do that, you will see that that agrees with the vector relations that we've written here. Okay, so same thing you can just think of in terms of a diagram also. So this is your XY plane. You can see in this given situation, X is located A is located somewhere here, let's say, at 3,0, and B is located somewhere here, let's say 0,4. So the position of A with respect to B and B with respect to A like this. Position of B with respect to A is a vector like this. And that is having a negative X component and a positive Y component. And similarly, you can see the position of A with respect to B is like this here. It's just the opposite of that. It's having the positive X component of 3 and the negative Y component, but both involve the same distance between them. This distance is D. You can see that D is equal to mod of RAB, or that's the same thing as mod of RB, which is 5. Okay, so now from position, we move on to displacement, the next definition. So from our earlier understanding of kinematics, we understand that if the position is changing, then the body or particle or whatever is in motion, has motion, and the displacement S at any point of time becomes the change in position. It becomes final minus initial position. This is the definition we've seen in kinematics earlier. So now in relative motion or relative kinematics, the relative displacement of one object, let's say B, with respect to another, becomes the change in position of that object with respect to the other. So relative displacement of B with respect to A in this case becomes equal to the change in the relative position again of B with respect to A. Okay. Now we'll take this another step forward. So since relative position of B with respect to A we've seen earlier is RB minus RA. So the displacement of B with respect to A becomes change in RB minus RA, which is delta RB or change in B's minus delta RA or change in A's position. So now using the general definition of displacement from here, we can see that the displacement of B with respect to A becomes the displacement of B itself in ground frame minus the displacement of A in ground. So this becomes the definition of relative displacement. And it's very similar to the definition of relative position. Just like RB is RB minus RA, like that S of B with respect to A becomes SB minus S. But remember, it's the vector difference. So just make a note of this.
What is the last time that you put in kinematics section?
Okay, so let's quickly look at an example. So two cars moving opposite to each other. Okay, along a straight road at constant speeds. Of 10 meters per second. Okay, cross each other at t equal to 0. Find their relative displacement after 10 seconds. So this is the situation at t equal to 0. So what is the relative displacement after 10 seconds? Yes, that's correct. Very good. No, just you made a mistake with the value better. Yes, Siddharth, that's correct now. Yes. So at t equal to 10 seconds, this car will be somewhere here, let's say. And this car will be somewhere here, let's say. You can see that this would have traveled 150 meters in this direction, whereas this has traveled 100 meters in this direction. Okay. So this is car A, let's say, and this is car B. So you can see with proper vector notation, one-dimensional vectors, we can just write them with sign. Or if we are writing them with unit vectors, so ultimately the conclusion you can see here is that in proper vector notation, S of A with respect to B is plus 250 I cap, and displacement of B with respect to A is minus 250 I cap. So the magnitude is 250. Okay, Akshat, so hope you have understood how to
Yes,
get
sir.
the vector difference. Huh? Okay. Now, similarly, let's look at another example. Now, at t equal to 0, two people, let's say P and Q, are at a common position on a horizontal plane. Now, at t equal to, let's say, 20 minutes, P has moved 120 meters east, and Q has moved 150 meters. At 53 degrees north of east. So you want to calculate the relative displacement of Q with respect to P. This thing we have to calculate. So you can draw a vector diagram also to understand this better, or So convert the given information, which is in terms of magnitude and angle and all this, or direction, into vectors in component form. It will be easier to solve. Okay. I cap नहीं आएगा बेटा. Okay. And any case now you have to tell the direction geographically. मतलब you know whether it is north, south, east, west, like that. You understanding the point? No? So
Yes, sir.
okay, so let's say I am taking my xy axis such that this is west to east, okay, and my y axis is south to north, and the origin is the common point from where P and Q both started. Okay, at t equal to 0. So P का displacement कैसा है? It is a displacement towards the east, you know, of 120 meters. So I can show it as a vector like this. Okay. So this is the displacement of P, or I can write it in component form as 120 I cap, okay, meters. But similarly, what is Q's displacement? Now you'll see Q's displacement is something like this. It is 150 meters at 53 degrees. Okay. So SQ will become 150 cos 53 I cap plus 150 sin 53 J cap. Yes. 53 degrees north of. So this direction is clear, na? 53 degrees north of east का मतलब ऐसा हो गया ना? So cos 53 is how much now? 3/5, and sin 53 is 4/5. So you will see that this vector actually little bit like this. So now the relative displacement of Q with respect to P will become like this. This is the vector. Okay, Parth, so this concept is clear, I hope, to all of you. Okay, people. So if you've understood this example properly, please, we can conclude the lecture here today. Any doubt in this, please let me know. So next time we will be discussing further about, now that we've discussed relative motion displacement, we will talk about relative velocity and acceleration and applications of the same. So this is for the next session. And with that, we will complete kinematics. Okay. Probably we'll take another session also to discuss questions and doubts. So start working accordingly to make sure you are in line to complete HC Verma exercise and also module questions, apart from the worksheets that I've sent earlier. Okay. That's it for today, people. Wish you all the best. And yeah, have a nice day.
Thank you, sir. Thank you, sir. Bye, sir.
Tanay, after this, in this track, we'll be doing circular motion.
Okay, sir. Thank you.